We have an RC circuit with 3 capacitors connected in series. The capacitors are initially charged and the switch is open. And then we close the switch. And the question is, what is the value of the current when the capacitors have lost 70% of their initial stored energy? The energy stored in the capacitor is equal to Q squared divided by 2C. Now, because the charge depends on time, this is Q as a function of time, and the energy is also going to be a function of time. And what's the formula for Q as a function of time? It's equal to Q0 times exponential of negative t divided by tau, tau being the time constant of the RC circuit. So when we square that, we get Q0 squared times exponential with a factor of 2 in its argument. Now notice that this expression right here, this is just the total energy at the beginning, right? At time equals 0, when charge is Q0, this is the energy stored in the capacitor. So this is the initial value of the energy stored. I'm going to call it U sub C 0 and rewrite my formula. And here's my formula for the potential energy stored in the system of capacitors as a function of time. Now, in the next line, I divide both sides by UC 0. So I get a ratio. On the left-hand side, I get a ratio of the current value of the energy stored in the capacitors divided by the initial value. So now we are told that the capacitors have lost 70% of their energy, right? So then this ratio of U sub C at this time divided by the U sub C at the initial time should be equal to 30%, because 70% of the energy is lost. The remaining energy is 30% of the initial energy. So in the next line, I'm going to substitute 30% and rearrange my formula to isolate T. So let's find the value for T first, and then we're going to calculate the current passing through the circuit. Here I have isolated T. Also in the last line, I have replaced tau, the time constant, with R times C equivalent. So let's go ahead and calculate the C equivalent, the equivalent capacitance for the circuit. The capacitors are connected in series, so we need to use the series formula. That's the reciprocal formula for combining the capacitors. Applying the reciprocal formula, we get equivalent capacitance equal to 4.9 picofarads. And then we plug in the numbers to calculate T, the time at which the energy drops to 70%. Sorry, energy drops to 30%. 70% of the energy is lost. So the time value corresponding to that is equal to 44 picoseconds. And again, pico is 10 to negative 12th. Here's the time-dependent formula for current. It's equal to the initial value of current I0 times exponential of negative t divided by tau. Now the initial current value is not given in this problem, but we are given the initial charge value, so we can actually express initial current in terms of the initial charge. Now initial current is equal to initial potential difference divided by the resistance R. And potential difference initially is equal to initial charge divided by the equivalent capacitance. So, and when we plug in the values, we get current equals 23.8 amps.